Hi everyone. So in this video we continue with chapter 4, exponential and logarithmic functions. Specifically section 4.2, the number e and continuous growth or decay. So let's recall that the function for compound interest is the following, right? A of t is equal to the principal times 1 plus r over n, and this to the power of n times t, where n is the amount of times it's compounded per year. Then, for the sake of simplicity, let's make p equal to 1. Let's make the rate 100%, and let's make the time period 1 year. So then we could rewrite this as a of 1 is equal to 1 plus 1 over n to the power of n, which is what we can see here. So really the question is, what happens if we compound this continuously? In other words, forever. So notice that if we compound it annually, it's going to give us 2. If we compound it twice a year, it's going to give us 2.25. 4 times a year would give us 2.441. 12 times a year, it would give us 2.613, etc. Daily would give us a figure of 2.714. Hourly, every minute, every second. So for every second, we would compound it 31,536,000 times a year. And that is going to approximate this number here. But this happens to be equal to E, which is Euler's number. So this table represents the values for 1 plus 1 over n to the power of n as n approaches infinity. So in other words, Euler's number is equal to the limit as n approaches infinity of 1 plus 1 over n to the power of n. Okay, so now let's take a look again at the formula for compound interest. So we have that a of t is equal to the principal times 1 plus r over n to the power of n times t. Now we're going to be switching some things around here. For that, we're going to say let m equal n over r. Now notice that this also implies that n is equal to m times r. So what I'm going to do is substitute for n over r and n into this function. So notice that this is going to make a of t equal to p times 1 plus 1 over m, and this to the power of m times r times t. So notice that I'm substituting this here for n, and 1 over m is the same as r over n, right? Notice that if I go 1 over m, that equals r over n. Okay, now we can rearrange this as p times 1 plus 1 over m to the m, and this to the power of r times t. But notice that this expression from the previous slide, we learned that this is Euler's number. So we could rewrite this as p times Euler's number to the power of r times t. So this gives us a very beautiful formula known as the continuous compound interest formula. Okay, so next we're going to take a look at example 4.6. And it says the starting balance of an investment account is 1,000 euros. The account earns an interest rate of 5.25%. Assuming there are no further withdrawals or deposits other than interest, find the total amount in the account after 10 years if the interest is added to the account. Okay, so that's just compounded interest. A, annually, B, quarterly, and C, continuously. So annually, that's going to be the case where n equals 1. And then we're going to say that A of 10 is equal to 1,000 times 1 plus 0.0525, and this to the power of 10. So this is going to be approximately, if you plug it into the calculator, 1,669.10 euros. Now remember that in these answers for questions regarding money, you need to have the right currency and you need to round to 2 decimal places. For B, it says quarterly. That's where n equals 4. So in this case, A of 10 will equal 1,000 times 1 plus 0.0525 divided by 4, and this to the power of 40. If you plug that into the calculator, you're going to get that it is approximately 1,684.70 euros. And then C, continuously. So that's where we use a formula for continuously compounded interest. So for this case, we would say A of 10 is equal to 1,000 times Euler's number to the power of the rate times time. So that would give us 0.525, and this is approximately 1,690 euros with 46 cents. Okay, so in the next slide, you're going to find a note about continuous exponential growth, or decay. If an initial quantity P grows or decays continuously at a rate R over a certain time period, then the amount A of t after t time periods is given by the function A of t is equal to P times e to the R times t. If R is greater than 0, then the quantity is increasing, growing. And if R is less than 0, then the quantity is decreasing or decaying. Now, let's take a look at example 4.7. And it says a particular new commercial jet costs $150 million. The aeroplane will lose value at a continuous rate. This is modeled by the continuous decay function. A of t is equal to 150 times e to the power of negative 0.053t, where A of t is a value of the aeroplane in millions after t years. Part A, find how much to the nearest $1 million the aeroplane will be worth precisely 5 years after being purchased. So that just means substituting 5 for t into the formula. So that would be A of 5 is equal to 150e to the power of minus 0.053 times 5. And this rounded to the nearest million is going to be $115 million. So notice that this is a rate that is negative, therefore decay, as it is pointed out in the problem. What would be the rate of decay? 5.3%. So let's take a look at B. And it says, if the airplane is purchased in 2020, determine the first year that the jet is worth less than half of its original cost. Okay, so that means that we have to set up an equation for this and solve for time. So we would say 150 times e to the power of minus 0.053 times t is equal to 75. Or in other words, if we were to solve this manually, we would say e to the power of minus 0.53t is equal to 1/2. Now, we could do this manually using natural logarithms, but since we haven't studied that topic yet, we're going to use the GDC. Okay, so here we are with the GDC, and we go to y equals. And what we do is that on the top function, y1, we would type in e, which is right here. We go second, and where it says ln, which is natural logarithm, we hit that and we find Euler's number. And then we need to put in the exponent, which is minus 0.053. And that times x. I just noticed that I'm missing a 0 here. So let me put that over here, 0.053t. Then we do the second function, 1 divided by 2. And let's hit graph. Okay, so notice that the window is not helping us very much. So we might have to change the scale. So we go to window and notice that we have a minimum of 10 for x. Let's make that 0. And then let's make the maximum 25. Let's make the scale, instead of 1, let's make it 0.1, since we have an equation that is equal to 1/2. And then for the y minimum, we can use 0, and we can use a small maximum of, say, 2, but let's not forget to change the scale for y as well to 0.1. So let's graph this, see if we have a better picture of what's going on. And yes. So what we need to do is find where these two graphs intersect. So we would go second, calculate, and number 5, intersect. First equation, yes. Second equation, yes. Guess. And there it is. It says that x equals 13.08 rounded to 2 decimals. So let's write that over here. It would take 13.08 years. So that means that it would reach a value that is less than half of the original cost in 2034.